Yeah, I guess before we get started, I should ask if there are questions on anything, anything that you want to ask me. Um, if you don't have anything, that's fine. Just know that you can interrupt me whenever you want. We'll go ahead with our plan of just finishing up this exam from fall 2017. So yeah, the link to that is going to be in the video description. It was in the previous recitation, so I think everyone can find that just fine. Okay, number 10. This is a, what's it called? Related rates problem? Yeah, I think that's what it's called. Rectangular fence, 3 sides. I'm not sure if we did a problem similar to this. This is definitely pretty standard among what we give, but for this semester, we might have, the problems might have been slightly different. I don't know. It's a good idea to check the type of problems that were given in the homeworks and also that were given in the past exam. Those will kind of tell you better like what variation is most likely going to be given to you, but this is I should say it's like pretty fair. So we have a rectangular fence, 3 sides that are let's make that look a little bit better. And the area, okay. So how do I want to do this? Well, we have a length and we have a width, and 3 of them are going to cost. Okay, we want to minimize the cost. So what I can do is I'll say that cost is equal to 2 times 2 width plus length. You can basically interchange length and width. So we're just going to choose one of the directions, and then the other one is going to cost. Oh no, my computer's being a bit. And then one of them is just going to cost 1 per meter, so we'll just have the other length, let's say. And the area has to be 12 square meters, so okay. And we want to find the dimensions that will minimize the cost, right? So that's effectively saying that we're trying to optimize the cost function. Minimizing is a type of optimizing, and in order to do that, we're going to need to replace one of the variables. Okay, what I'll do before that is I'm going to expand this out just to make it nicer. So 4W plus 3L. Okay. It doesn't look like it matters which thing I replace, so I'll just let's say that I substitute out the L then. So 12 over W. So then C is going to be 4W plus 36 over W. Yep. Okay, and this is the function that we want to optimize. View cost as a function W. Right, so then the derivative is going to be 4 plus, well, not plus, minus. Okay. 4 minus, okay, let me do something really quick just to maybe make my computer run a little bit faster. Okay. Okay, minus 36 over W squared. So that's the derivative. We would normally set this equal to 0 and solve, which is going to give us 4W squared is equal to 36 which gives us W squared is equal to 9. So then W is equal to 3 plus or minus. But then we obviously would choose the positive solution. And if W is equal to 3, that tells us that the length is going to be equal to 4 meters just by using the equation L is equal to 12 over W. And so this should be the dimensions that would minimize the cost. One thing that we do that doesn't seem to be specified in the problem statement, but I would guess you should do, is to make sure that you have some kind of justification that this actually gives you a absolute minimum, right? So because as the process that we've done here only shows that this configuration gives rise to a local minimum, but we still have to say something to guarantee that it's actually an absolute minimum. One thing that we can do for that is, well, the way that the problem is structured, W can, you would use the possibility of W going from 0 to infinity, because the main thing that limits the configuration is that the length times the width is equal to 12. And with this kind of constraint, what happens is you can make W really minuscule, but make L really large, or vice versa, make W really large, but make L minuscule, and you'll still have the balancing of those two things out to make the area equal to 12. That's why the natural domain for W is going to be 0 to infinity. And then from that, you want to use, what's it called? First derivative test for absolute extreme values. I guess that would be one, that's one thing you could do. The other thing, you could try to use a second derivative test. Yeah, actually here it's fine because the 4 is going to disappear when you take the second derivative, and you'll end up with a positive thing. So maybe we can do that. Take the second derivative and we'll see we get negative, I think 72, no, positive 72 over W cubed. And the fact is that this is always positive, which by the second derivative test for absolute extreme values, it's the second derivative being always positive for your domain in question, which is W being from 0 to infinity. That means that this local min is actually an absolute min. So yeah. The absoluteness is what is the thing that we're seeking. So yeah, and then probably to box the configuration that we're actually trying to find. So width is 3 meters, length is 4 meters. Okay. Continuing, estimate the area below the curve over an interval using R is equal to 3, right endpoint. And it wants us to graph this. Well, that's fine. I'll start by plotting the graphing it. So when we go over to 1, that should go to 3. When we go over to 2, that should go, I want to say up 3. 1, 2, 3, 6. Is that right? Yeah, 4 plus 2. Okay. And then 9, 11. Yes. And then 4 is off the graph. Okay, so that's approximately what the graph looks like. And we want to use 3 rectangles. So that's pretty easy to do. The rectangles all are going to have width of 1. And we want to use the right endpoint approximation. So that means that the height of the rectangle is going to be given by the height of the right endpoint of each of the subintervals. So this rectangle from 0 to 1 takes the value at 1, 1 to 2 takes the value at 2, and 2 to 3 takes the value at 3. And so these are going to be the rectangles that you sketch. And to calculate the area, well, yeah, this approximation is, I'll put the 1 in front just because, like, in general, the rectangles might not have a width of 1. They could be, any width. You just have to make sure that you divide the total length by the number of rectangles, and that'll be the size of the rectangle, the width of the rectangle. Okay, and then 3 plus 6 plus 11, those are the different heights, and that's gonna give you 20. Okay. Not 20. No, just 20. Yeah. Okay. All right, integrating. So let's see, how many integrals do we have? Just 3. Okay. So the exponential, that should remind you of, like, it's a simple u sub. You could use u equals 5x, or you could be familiar enough with it and notice that, like, by guessing this and then taking the derivative, what you end up with is 5 times e to the 5x. So the extra 5 that comes out from chain rule needs to be canceled, which means all you have to do to adjust the answer and get the right antiderivative is just dividing by 5 up front. So now this guy is going to, when you take its derivative, equal to e to the 5x, and that's the first term. The second term, you need to kind of pattern match it, go through this should remind you of the inverse trig functions. And the one that this matches is arctan, or no, not arctan, arcsine. But the problem is arcsine, you have to adjust this a little bit because I don't know if we use this technique at all in class. Normally, well, I'll write the derivative rule. So inverse sine of x, when you take its derivative, is 1 over root 1 minus x squared. Okay, so this 1 is important here. Notice that that's a 4, not a 1. So to deal with this, what I'm going to need to do is actually turn this 4 into a 1. And the way to do that is actually by dividing by 4 inside of the integral. What that's going to do is it'll then, I can make it resemble this format, but then require a u substitution. Technically there is like a more general formula, like a squared minus x squared. If you can memorize that formula, that is one technique that people do, but I can never remember, especially because there's a very similar formula for arctan, a generalized arctan with like x squared plus a squared. But then the problem is they're similar but not completely the same, and so I can never keep them straight. But the technique for actually deriving the formula is reasonable, so that's what I would do. So I'm going to go through that technique, I guess, on the right-hand side. So like I said, you factor out the 4, and that's going to end up giving you an x squared over 4. And I may as well regroup that now so that you have x squared, x over 2 quantity squared. Okay, right? That should be pretty clear. And then what we have to do is rewrite that. I can bring the 4 out of the square root now. It's kind of in the way that it is. And bringing it out of the square root, I have to take the root of it. And we have this. Okay. So all I've done is I've just algebraically rewritten this expression. So the problem is actually, I don't want to write it things that are too much scratch work, like let's pull the 2 in the denominator out of the integral. And so now, there we go. So we've turned this integral, or the integral of this term into this integral. So we just need to compute this integral now. And this guy really does resemble the inverse sine formula, except you have to apply a u sub to it. Okay, so let's go ahead and do the u sub. U is equal to x over 2. Du is equal to 1/2 dx. Okay, well that's convenient because we already have the 1/2 in front, so I can just pull that. I can kind of pull that back in when I do the substitute, when I perform the substitution. Performing the substitution, I'm going to end up with this. And so now we know that this is inverse sine of u, which is equal to inverse sine of x over 2. Okay. And we didn't account for the minus, so the minus is actually there in the answer. And so we can finally write down the answer completely. There we go. Yeah, so inverse sine apparently behaves like this, whereas inverse tangent, if you had like a similar thing to that, inverse tangent, I guess, is the one that has the 1 over the number in front. I could check that, but I don't know. So if someone catches a mistake, just let me know. It's kind of possible that I could make a mistake, but I haven't done these beforehand. B is also a u sub problem. Hopefully you could kind of spot that immediately, right? You see that the inside is the same between the sine and the cosine, and you know that sine and cosine are derivatives of each other. So that should immediately like make you think of letting u be one of them. And the one that would make sense here is letting it be sine, because then you'll have u raised to the 5th power. So we let u equals sine of 2x. And so then du is going to be cosine of 2x times 2. And then we would have a dx. Okay, so there's an additional 2 that we need to account for. And we'll do that. We'll handle that in the typical fashion by introducing a 2 by multiplying and dividing. Okay, and so now you see that the 2 cosine 2x dx, all of that is going to be absorbed into our u sub as du. And then the sine to the 5th of 2x, that's going to become u to the 5th. And so our integral turns into a much simpler integral to evaluate. And we can go ahead and just do that. And then we would have to back substitute. So raising u to the 6th power, I may as well just write this as sine to the 6th, and then 2x, and then of course plus c at the end. Okay. All right. Right. Part C. So this also is a u sub. Right. When you see the ln and you see an x in the denominator, you can kind of immediately spot that. That's a very common pattern. Hopefully, if you've done enough like u sub problems, you would get a hang of the patterns. So let u be ln of x, then du will be the 1 over x, and that dx, and that will resolve all the complexity of this problem. Make that look like an x. So the ln of x squared, that's going to become u squared, and then the over x dx that gets turned into du. Now we should also convert the limits of the integral over, and we of course plug them into the substitution that we're applying. So letting u equal ln of x, the limits are x equals 1 and x equals e. We convert them into u equals, and in this case, ln of 1, as you should know, is 0, and ln of e is 1. So those are the limits of our new integral. And then we can go ahead and integrate that. So then get x cubed over 3, and then we evaluate from 0 to 1. Well, that's just going to be 1/3. 1/3 minus 0, but that's 1/3. Okay. Right. Okay, next. All right, so this is just an area of between two curves kind of problem. Okay, so this parabola, I want to factor that, and I'll get x times x minus 2, which means that the intersection points of the parabola are there and there. I know it's opening upward. The fact that it gives me a grid makes me want to actually try to graph it a bit closer to. Okay, if I plug in 1, I get 1 minus 2, so I get -1. And right, and then okay, so 1, 2, 3. So the next one's here. 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the next one will be like up here. That's fine, whatever. Okay, the line 6 minus x. So that's another line, 6 minus x. Fine. Okay, great. So it goes like that. But oh, okay, with x being greater than or equal to 0. So yeah, so this is also a bounding thing, part of our graph. So the one thing that could happen if you're not careful with graphing the thing is you could actually have it be like a parabola minus that, and then you'd have a piece of it which would be to the left of 0. But in this case, it actually, the problem explicitly says that we're only considering the part of the region where it's x is greater than 0. Also bounded by the y-axis. Okay, yeah, okay, that's just being redundant, but that's fine. And we want to calculate the area. Okay, so yeah, so we have everything we need. So this would be the area, and as you should know, the way we calculate it is we do upper function minus lower function, and we swipe across one of the standard directions. So in this case, we want to swipe across the x-axis. So our integral is going to go through is going to sweep across x from 0 to the intersection point, which is 3. Right? Maybe it's more illustrative to actually draw the segments that you would get. So yeah, as you sweep across the x-axis, you have like these small things. Think of them as like infinitesimally thin rectangles, because as you know, like an integral is technically a Riemann sum, which is a sum of infinitely many rectangles. And so viewing it like this, we're just sweeping across the x-axis, and we're just counting the heights of all these rectangles. And so it's upper function minus lower function that will give us the heights of each of those rectangles. And I'm going to need a little bit more space actually to write it out. So upper function in this case is the line 6 minus x, and the lower function is the x squared minus 2x. Okay. Well, this is just going to end up being a polynomial, so integrating is going to be pretty straightforward. And I may as well rewrite it in kind of the standard order. 2x minus 1, so plus x and then plus 6 dx. And then that's going to be negative x cubed over 3 plus x squared over 2 plus 6x. And then we would evaluate this from 0 to 3. Right. Well, plugging in 0 is really easy, which is always a good thing for doing these things, problems. Okay, then plugging in 3, I have -9 plus 9 over 2 plus 18. Right, so that's 9 plus 9 over 2, 18 plus 9, so that's 27 over 2. Okay. So that's the area of the shaded region in red. Okay. Next, 14, we have an initial value problem. So we have this derivative and we have basically, well, yeah, what it means by solving an initial value problem is it means to find what is the function f of t in this case. What is the f of t that satisfies these conditions? So we have information about the behavior of the function's derivative, and we have information about a single point that lies on the function. And this kind of harkens to differential equations when you actually, if you learn that subject. Initial value problems are kind of the bread and butter of that subject. Okay, so finding the f of t, well, what you would do is, I really don't want to write it like that. Well, maybe I'll just, yeah, I can just write it like this. dt. And so, right, we need to integrate this guy. This is going to give us t to the 4, and then the minus sign, so that's going to be cosine of t. And then normally you would have the plus c there because this is a indefinite integral. You don't have limits on this guy, so you have a constant. But what happens is that this initial condition, this point that lies on the function, it specifies what the constant has to be. So what we can do is we plug into the function. So f of 0, in this case, would be 0 plus cosine of 0 is 1. So 0 plus 1 plus c is equal to 1. Okay, so that tells you that c must be 0. Okay, so that was kind of a very easy situation. Normally I would engineer the problem to not have c be a 0. I would have it actually be some number. But yeah, so here it's 0. And the very last step is you want to rewrite the function without c, but with the actual value of c, which in this case is just going to be that. Okay, and so that is the solution to this initial value problem. And I mean, one way you could actually, if you weren't confident about it, you could check just by checking that both of these conditions hold for this function that you've found. Right, you plug 0 in, you should get 1. You take its derivative, you should get back to this guy. That's how these kinds of things work. Okay. Linear approximation. So that goes back quite a bit. Maybe it was the first exam. Maybe it was the second. I don't remember. But yeah, so linear approximation, the first thing that you should think of is the formula for linear approximation. So that's f of a plus f prime of a times x minus a, right? This is just kind of a dressed up version of the point slope formula, right? You have f prime of a is the slope, this x minus a is kind of the thing that you're used to. And then this f of a, this is actually the y naught, right? So this would be like y minus y naught is equal to m x minus x naught. So it's just a dressed up version of that. And what we need to do is we need to construct the actual approximation for this particular function for this particular value of a. So we can go ahead and do that. I guess I'm okay with just rewriting it as the way that it is. So here, yeah, a is equal to 9. This is going to just be the square root of 9, which is 3. F prime, I have to do a bit more work just to make sure I get it correct. So 1 over 2 root x, that's the derivative of square root of x. You could think of that as just being an application of power rule, but the way I remember is just like by taking this specific function so many times, you kind of get used to the fact that that's the derivative. And then f prime of 9 is going to be 1 over 6, 2 times 3. So we get 1 over 6 and then x minus 9. Right? I need to substitute that a value in. Okay, so this is the linear approximation, and I'll just rewrite L of x so that I can box the whole thing on one line. Okay. And now we have the application of this linear approximation. We want to approximate the value of the square root of 8.9. And so the idea for linear approximation is that for values that are close to where you centered your approximation at, the linear approximation should be kind of close. And 8.9 is pretty close to 9. So the idea is you can approximate this by taking L of 8.9. And so let's go ahead and try to plug that in. 3 plus 1 over 6, 8.9 minus 9. Okay. If I do this subtraction, I'm going to get I'm going to get -0.1. I really don't like that. I don't like it because it's not a clean decimal value. But I don't think I made any mistakes here. No, I'm pretty sure I didn't. Okay, well, then in that case, I'll just write it as a fraction instead. It's a bit weird. I mean, you could figure out the decimal value of 1 over 6 and then send the decimal over. 18 minus 1, so 17 over 6 is what I'm getting. I should know what 1/6 actually is. I think it's 0.1, it's 0.186 repeating, I think is what it is. I think that's what it is. But anyway, yeah, so I'll just stick with that. Yeah, if you wanted to, you could figure out what that decimal approximation is for that. Okay. No one is complaining about that, so I guess everyone's fine with it. Oh, this is the last problem. Okay. Sketch the region bounded by the y-axis and the line y equals x, and another line. Okay, another line. That's interesting. So y equals x, that's easy enough to draw. And then 3 plus a half. So that'll be like that. And it'll intersect there, and then it'll go through. Okay. Find the indicated volumes. No? Oh, wow. The problem is actually giving you points just to sketch it. That's funny. The y-axis and that. Okay, that's fine. So volume by rotating the region about the y-axis, just set up the integral. You don't need to evaluate. Okay, great. How do I want to mark this? Maybe, so this is going to be for part B. For part B, we rotated about the y-axis. So if we wanted to set this up, the thing is that the segment that we would track, I would want to draw it like vertically. I would want to draw the segment vertically. And that tells me that we're dealing with shell method. Okay. So we would set up the integral using shell, the formula for shell method. So we have a 2 pi in the front. We have an integral. In this case, we're going to vary over x because our segment that is in green, a bit hard to see, but there it is. It varies over x, going from x equals 0 to x equals 6. So that tells me I could probably just write the whole integral in green. That's fine. Yeah, it's fine to do that. 2 pi integral. We vary over x. We go from 0 to 6. And we have two things inside the integral. We have a radius function and we have a height function. The radius function here is the easiest case because the axis is not off center. It's not off of not off of the standard axis. So like this particular segment, if it was a distance x away from the axis, it would be a distance x away from the axis of revolution. Two different axes, two different lines that I'm talking about there. And then the next thing that we need is we need the height function. So that's just going to be the top minus the bottom. So in this case, the top one is the 3 plus 1/2 x. And then we subtract x. And we could just leave it as that since the problem doesn't ask to evaluate it. So I would probably just leave it like that. Right. So not needing to evaluate, that's just a time-saving measure. It's kind of expected that you would know how to integrate this kind of thing. It's pretty straightforward. This is a polynomial. For the other one, let's see. The part C, I guess I'll use the other color I have here, which is red. So in this case, we want to rotate it about the x-axis. And yeah, I want to use the same segment. So let's just draw it somewhere else. But if we treat that as our segment now, notice what happens when you rotate it about this axis, you end up getting a washer. So this is going to be the washer method, which is radius squared minus radius squared, big radius squared minus small radius squared, right? As you know, that's how you would calculate the area of said washer. And then on the outside of your integral, you have pi. And let's see, x is going, we integrate over x is going to vary from 0 to 6 in this as well. And we just have upper function minus lower function. So upper function, again, is the 3 plus 1/2 x squared. And then the lower function, the smaller radius, that's the y equals x. So that's just a function x. And so there you go. That's the other integral. And evaluating it is also pretty straightforward. You would just have to expand it out and then integrate it as a polynomial. Okay. And so that's it for this exam. Are there questions on anything? You can feel free to ask anything you want. This is supposed to be review. No one has questions. Okay, well, we're a few minutes early. I guess we can stop here. Good luck on the exam.